Good morning and welcome. Today we are going to enter into the field of binomial expansion, learning about Pascal Triangle as a tool for expanding binomials. In the course of this lesson, we are going to learn the meaning of binomial expansion. We are going to learn to draw a Pascal triangle. We are going to learn how to expand binomials using a Pascal triangle, and we are going to solve examples on expansion of binomials. So what is a binomial expansion, or what is a binomial first of all? A binomial is any algebraic expression of the form a plus b, where one of them or both of them are unknowns. So when you have x plus 2, y minus 4, 5 minus w, those are all binomials. It means two terms in an expression. Now when we have a binomial expression raised to the power of n, where n can be either 1, 2, or 3, it is still a binomial. To expand this binomial, we can use several methods, and this is known as binomial expansion because it follows a specific rule. And one of the methods which we can use in expanding this binomial is the Pascal triangle. Now, studies from several mathematicians have showed that expanded binomials follow a certain pattern. This pattern allows us to expand binomials without multiplying them. Normally, if you were to expand a binomial, you will need to start multiplying. Given that example from the first slide, if you were to expand this a plus b and it was raised to power 2, you will have to do a plus b raised to power 2 times a plus b raised to power 2. However, using the rules of binomial expansions, you would not need to do this. You can just apply the rule directly and expand the binomial without the need of multiplication. So, one of the simplest representation of this expansion rule is the Pascal triangle, where we draw a triangle by writing several lines with the number 1 at the edges, and we get the number below it by adding the two adjacent numbers. Now, this is easier to understand in practice. So let us look at this. This is an example of a Pascal triangle. Here we have 1, 1. So we have 1s at the edges. Every new line starts with and ends with 1. To get the number in between, we add these two. 1 plus 1, 2. So here we have 1, 1 plus 2, 3, 2 plus 1, 3, 1. 1, 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, 1. 1, 4 plus 1, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, 1, and so on and so forth. This is how a Pascal triangle is drawn. Now, how do we use a Pascal triangle in solving a binomial expansion? The Pascal triangle gives us the coefficient of the terms in the expansion. The two terms in the parentheses are then multiplied and placed after the coefficient, with the index of one increasing from 0 to n, while the index of the other increasing from n to 0. For example, here we have a plus b squared, giving us coefficient of a 1, coefficient of ab 2, coefficient of b squared 1. So we can see the coefficients follow 1, 2, 1, which is the second line of the Pascal triangle. And here we have no term b here because the power of b is 0. The power of b here is 1, and the power of b here is 2. So the power of b increases from 0, 1, 2. While the power of a here is 2, the power of a here is 1, and the power of a here is 0 since a is non-existent. So the power of a decreases from 2 all the way to 0. The same thing we can see here, Our coefficients are 1, 2, and 1. The power of x is decreasing from 2 to 0, while the power of 5 is increasing from 0 to 2. So this can be used in expanding any binomial or making the expansion of any binomial very easy. If you had a plus b raised to the power 10, for example, it will be very easy to use your binomial expansion or your Pascal triangle to expand it rather than multiplying 10 different times to get your result. And you know, when you multiply so much like that, a single mistake can lead to disaster. So when n is equal to 1, that's when the power we are raising the bracket to or the parenthesis to is equal to 1, our coefficients are 1 and 1. In other words, nothing changes. Remember that when you raise anything to the power of 0, it is 1. So if you have a binomial raised to the power of 0, you get 1. When you have a binomial raised to the power of 1, you don't multiply it by anything, since any number multiplied by 1 is that same number. So the binomial remains the same. When you have a binomial raised to the power of 2, you will have 3 terms with the coefficients 1, 2, and 1, as I showed you in the example. When you have a binomial raised to the power of 3, you have the coefficients 1, 3, 3, 1, and 4 terms all in all. When you have a binomial raised to the power of 4, you will have 5 terms with the coefficients 1, 4, 6, 4, 1. And when you have a binomial raised to the power of 5, you will have 6 terms with the coefficients 1, 5, 10, 10, 5, 1. This is what a Pascal triangle represents, and this is one of the applications of a Pascal triangle. I hope you were able to learn something new today. Here is another representation of a Pascal triangle and an easier way of remembering them. Looking at it this way, everything here is 1. Also, everything here is 1. Looking at the second line, everything here is a counting or natural number. We have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And everything in the third line is a triangular number. That is the number of boxes you will need to arrange a triangle. Here we have 1. Here we have 1, 2, 3. Here we have 1, 2, 3, 4, 5, 6. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And continue, we have 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So that is another way to find out if your Pascal triangle is correct. Here are some questions. Draw a Pascal triangle to n equal to 8, and then using it, expand the following: x plus 3 raised to power 3, 5 minus x raised to power 5, and then 2x minus 3 raised to power 4. Thank you for watching, and see you